Hi, my name is Dan Gilliland. This is our last lab of the semester, magnetic braking. For a bit of an introduction, the purpose of this lab is to experiment with the time-varying magnetic field due to a, quote, curly electric field by observing the interaction between the falling magnet and the tube of aluminum foil and the result from that. Just a preview of the final result. The actual time that the magnet took to fall was 7/10 of a second, and the time for my computational model was 0.734 seconds, which is pretty close considering all the variables. Just to add on to the intro, the main physics principles used in this are Biot-Savart's magnetic field of a dipole, which we just kind of use for the bar magnet here, magnetic flux, and its differential with respect to time, Faraday's law, Lenz's law for magnetic field of induced current, and Newton's law we use for velocity. In this experiment, I used the calculated magnetic dipole moment mu from a previous experiment that we did, and I found it to be 4.428 Newton meters per Tesla. We can't use a ferrous tube because the magnet would immediately stick to the inside of the tube. When we drop the magnet down the tube with aluminum foil, it slows down the magnet compared to when you drop the magnet just free fall. The free fall time, which I also did for 5 trials and measured the average, was 0.37 seconds compared to our time through the tube of 0.7 seconds, which is basically double. In this slide I have more important parts of the code for the computational model that we used. Here we got geometry of our tube, the definition of our function for the magnetic field due to our dipole, again defining our function for calculating flux, which is then used later on in right here. Then right here we have a conditional statement to determine the colors of the rings with respect to the current in them. And here we have the calculation for our typical magnetic field at each ring. And then lastly, we are using these to determine the magnet's velocity and position at a certain point in time. Results from my code. The actual time, like I said, is this 0.7 seconds, and from the computational model we get this 0.73 seconds, which is pretty darn close considering all the variables. You can see from the graph that at first the velocity was changing, acceleration. There was acceleration, and then acceleration fell to 0 and velocity was constant, and then it started accelerating again. What if? Questions. What if the resistivity of the conductor was reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, as the resistivity approaches 0, the force pushing the magnet up increases and stops the magnet completely canceling out the force of gravity. I entered in a number close to 0 into the computational model, and the graph asymptotically approaches 0 for velocity. What if holes or slots were cut into the tube? How would this affect the ring currents in my model? The braking force wouldn't be as strong, making the magnet fall faster. This would be disruptive to the normal flow of the current through the rings. Interpreting the simulation, the intensity of the coloring on the tube indicates the magnitude of the flow of the current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current as viewed from above, and which counterclockwise? How can you know? Blue represents counterclockwise and red represents clockwise from Lenz's law. What happens to the dynamics of the system when you flip the magnet around? Nothing observationally would change, but the current would flow in opposite directions. How does the total time in the tube of my real world system compare to the computational? Well, and how might the computational system be made more accurate? Well, we could account for air resistance, we account for, could you be using better tools for measuring more accurately, or account for any outside the system fields that could be affecting our results. Our results are pretty similar. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The forces are unbalanced for a portion at the start and the end, but in the middle of the speed is constant for approximately 0.6 of a second.